as I said on the internet chat, we're having quite a bad thunderstorm here. So if I lose electricity, I'm afraid I'll disappear. So Josh could pick it up or TJ could pick it up. Just let you know that if I disappear, that's what's going on. Pretty bad storm right at the moment. So today I would like to continue by talking about modeling of viral infection dynamics. And to do that, we're going to have to do a little bit of ODE modeling, of Tellurium modeling. And we're going to be using the Jupyter Notebook Tellurium tool on nanoHUB. And we'll come back to that. People probably, if you took Herbert's class last week, you'll have used this tool already, but we'll remind people of how to do that. And this lecture is probably a little bit long, and so we don't have to go through all of it. The key thing is that you understand the core ideas and do some of the exercises, and then you'll be able to download the finished model. In fact, you'll have the finished model from the beginning because we'll have it uploaded with you. And you can work through the extra exercises and slides on your own if you want to. Again, there's quite a bit of detail here that we probably don't need to cover completely. So I'd like to, all right, so the module that we're going to cover today is going to start by reviewing how to run Tellurium on nanoHUB. We're going to do some uploading files. It's easier with Tellurium because they're single files rather than packages. We're going to talk about how to define antimony models as strings in Python, running them, how to do simple parameter sweeps, and then we'll talk a little bit about the dynamics of viral infection, how to build a basic model of viral infection and immune cell clearance. And we're not going to do any formal parameter fitting. With Herbert, last week you learned how to do parameter fitting in Tellurium, but we're going to do some hand parameter fitting. And then if people are interested, they can refer to Herbert's lectures on the details. Andy Samoji maybe will help us out with that a little bit as well. Again, since the purpose of this class is to focus on the CompuCell side of it, we're going to have to go through the ODE side a little bit faster. Again, the workshop resources are in the usual places. I hope you can find them all right. The key thing is going to be finding the files to upload for the demos. We're going to be talking about dynamics of viral infection. There are a variety of patterns of viral load. We're going to be focusing essentially on the amount of circulating virus in the tissue. Depending on the particular virus you're talking about, you can have what's called monophasic response, where the viral load goes up, saturates, and comes down in essentially a U-shaped, almost an inverted parabola. You can have a biphasic decay, where the virus goes up very quickly, then goes down slowly, and then goes down quickly again. That's the one we're going to focus on today. Triphasic, the virus comes up, goes down partially, stays at an intermediate level for a while, and then clears. That one we're not going to discuss so much, although it may be the one that's most relevant to COVID. And then there's also what's called biphasic decay at the end, in which case you don't clear the virus. In our cases, we're going to assume that we're going to clear the virus. In humans, at least, to recover from a virus, you have to clear it. But there are certainly viruses like HIV that you never clear and you can live with. And in many animal models, for example, bats often don't clear viruses, they live with them. So that last one is certainly possible. There have been a very large number of ODE models of these processes. We'll talk about a couple of them in the next slide. But the basic idea here is that you have some set population, these are population models, a population of infectable cells, we'll assume these are long epithelial cells. Those cells can be infected by the virus, becoming early infected cells. Those are cells that have virus, which is beginning to replicate inside of them, but haven't yet released virus into the environment. Late infected I2 cells that are viral cells that are actually actively releasing virus into the environment. Those cells can die from the production of virus and from other means. The virus itself will decay in the environment and also potentially be scavenged. We heard about phagocytosis. Can be bound by antibodies. In many ways, the virus can be cleared. So that's the basic concept. There are many, many models of viral infection for many different viruses. There are some that are very, very detailed. For example, this one of Price, that's a model of influenza that includes many specific immune system components. There are also some very simple model structures. Alan Perlson, one of the great mathematical models of virus, likes very simple model structures. And there are a variety that are intermediate. This is another model by Amber Smith in University of Tennessee and Alan Perlson as well. And if you looked at these models and traced them in Google Scholar, you'll find hundreds and hundreds of models of this kind. We're not going to use a purpose-built or a pre-built model here. We're going to talk a little bit about the principles of building one. The model we're going to come up with will do a pretty good job of fitting to the data, but it's not going to necessarily be the best model from a mechanistic or biological point of view. You may want to think about that. Okay, so we're going to start building an ODE model of viral infection. And then what we're going to do over the next few days, we're probably not going to get to start on the CompuCell part of this afternoon. We'll start tomorrow morning. So that means module 1.6 will be delayed till tomorrow morning, unless people really want to stay for an extra 2 hours. We'll see how far we get. Okay. Will involve taking that ODE model that we're going to run in Tellurium, running it inside of CompuCell. So we have the exact model that we've just written running inside of CompuCell. So we know exactly what it does. And then step by step, we're going to take all of the concepts that are ODE concepts and turn them as appropriate into spatial concepts. And ask the question at each step, what's different? We're going to be sure that in the limit that the spatialization is weak, for example, infinite diffusion constant, that we recover essentially exactly our ODE results. That means that everything we see that's different is going to be an explicit consequence of the spatialization. That means we can really say definitively why we need to have a spatial model. Of course, if everything winds up being the same no matter what we do, then the answer is that we can stay with the ODE model. We don't have to go to the spatial. Okay, so we're going to start out by building a model in Tellurium. I hope that some of you have been able to do this last week, but again, I want to be clear that we're going to go through everything step by step here. So even if you didn't take Herbert's class last time, you'll be able to get, I hope, catch up with that too. So the first thing we're going to do is launch Tellurium on nanoHUB. I think you're used to launching things on nanoHUB. If you want to go back to your desktop here, you go up here and can people see? I can't see what you're seeing, so you have to tell me. If you go to the desktop here, you should be able to go to your desktop. And then in desktop, if you don't have it already, type Tellurium. Into the search bar. Okay. Everybody got that? I don't hear any objections, I'll assume people are able to find it. I recommend favoriting it so you know how to get there, and then launch it. Okay. Has everybody gotten to the Tellurium launch window? I'll do a poll quickly. A quick poll. Has everybody gotten the Tellurium window working? For the remainder of the afternoon, we're going to be working in Tellurium, so it's important to be able to get it up. Is somebody having a problem? Somebody said they couldn't, it's not working. You can also run Tellurium on your desktop if you prefer. I'll give people just another minute to launch. Everybody okay? Okay, I really encourage you to use nanoHUB. If you haven't downloaded the Tellurium library specifically, you can't use it. You have to have the Tellurium library. So if you have a regular Python IDE and you don't have Tellurium, you'd have to go to Herbert's Tellurium homepage and download the software. So again, I want everybody to, and you certainly can run Tellurium on your desktop, but you need to have the library, just the way you need NumPy or any other Python library. And so if you haven't downloaded that library, you won't have it. Again, I understand nanoHUB isn't always the most convenient thing in the world, but it does have the advantage that you don't have to download packages and install them. And since we don't know everybody's computer configurations, using nanoHUB is a compromise. It's not the most elegant thing, but at least we don't have to debug everyone's computer all at once. In past years, when we've done that, it can be a little chaotic. Okay. All right. So now that we're in Tellurium, what we're going to do is, you'll notice up at the top here, there's a note that says read only. There's a note that says read only. That's a bug in nanoHUB Tellurium. You can fix it by going to File, go to New Notebook, and select Python 3. And now you'll get a window that says nanoHUB, and it no longer says read only, but the import Tellurium as TE has disappeared. So type import Tellurium, did I spell it right, as TE. And I always recommend having NumPy available, so I would say import NumPy as NP. Okay. And then to execute a cell, you can either go to cell and say run cells, or if you click inside of the cell, you can hit Control Enter or Shift Enter to execute the cell. And if there's an error, a syntax error, it'll throw an error underneath the cell. Okay, does everybody have that? Oops. One problem with sharing the desktop is that if it throws a random window up on the screen, you get it. But to be able to show you both windows at once, I need to share the desktop. So I apologize if there's an occasional spurious window that comes up. Okay, good. So now we are going to go, and we have Tellurium running, and we're going to upload the demos that we're going to run today. So just as before, you're going to go to File, select Open, and do Upload, and you're going to navigate to CC3D course, Student Materials, Workshop Exercises, and Homeworks Exercises, Lecture 1.5. Everybody got that? You want to make this text in the notebook a little bit bigger, I can do that. As soon as we've done the upload, I'll make the text bigger. And now select exercise 1.5.0, open, hit upload. It's here. Double click on it to open it. Is that better for viewability? Okay, does everybody have this window running? Does everybody have that?
Could you go through that load procedure again? You went through the file menu so quickly that I don't think anybody got where they're supposed to be getting this file from.
Okay. So you're going to go, you've got Tellurium launched. You're going to go to Open, Open, Upload, and it is Google Drive, CC3D course, Student Materials, Workshop Exercises and Homeworks, Exercises Lecture 1.5, Exercise 1.5.
The file can also be downloaded from the link that I posted in the chat directly from Slack.
So people have to first go and download the file to their local machine before you can upload it into Tellurium.
Is everybody able to find this? Does anybody have trouble finding this file? It's in the Google Drive. If anybody needs help, Josh, could you post the link again to the Google Drive?
Yes, 1 second.
Okay, just let me know if you need extra time or help with this.
Well, the big thing is you can't directly download from Google Drive from within Tellurium. So people have to download that zip file.
Is anybody having trouble with this? If you are, let me know. The file name is exercise 1.5.0.ipynb. And we'll have plenty of opportunities to do this again. So if there's an issue, we can come over it again. Okay. No, don't use the zipped directory. Use the unzipped one. It's unzipped, not zipped. So again, if we go to student materials, so this is CC3D course 2020. Student materials, workshop exercises and homeworks, exercise lecture 1.5, not zipped, exercise 1.5.0, open. Okay. Does anybody still need more time? According to my poll, almost everyone has it, but if somebody needs help with that, let me know. Okay. If you're having trouble, please send a text message to Jim Sluka or Josh, and they can move to a breakout room and help you with it if there's a problem. All right. So once you have this file loaded, double click on the file, and it will open. And you should see this. So let me check and make sure that everybody has this running. Is everybody able to get to this screen? Okay, that's great. If somebody could tell me how to keep the poll from jumping up on that window, I'd be grateful. But that may take more doing. Okay. Great. I'm glad everybody has it. Okay. So you should have a directory that looks, a file window that looks like this. There's a text box here that says we start with a population of uninfected susceptible cells, T, initial number T0. Infected cells become infected, I1 cells, at a rate that's proportional to beta times the number of T cells times the number of the amount of virus. We're going to assume that the amount of virus is constant here. And now we're going to build a teeny little model, Tellurium model, which we're going to run. So this is going to be very much a review for the people who took the class last week. For people who haven't taken the class last week, this may be a little bit new. And so we'll quickly go over how this works. First, if you need to find out about Tellurium, you can find references for Tellurium. There's a very good online documentation, tellurium.readthedocs.io, excellent online documentation. There's also in our online materials a cheat sheet, which is a one-page summary of all you need to know for Tellurium. It's really simple, which is why we use it. And so please take a moment to find those documents. Josh, maybe you could post those two links into the chat and the Slack. All right. So we're going to build a one-line model of viral infection, not a very elegant one. We're going to say that a virus, V, the virus V infects the infectable cells T, turning them into early infected cells I1 at a rate that's proportional to the number of T cells the rate beta, and the amount of virus. And we're going to assume that the virus isn't used up when it does the infecting. In reality, of course, the virus is used up when it does the infecting. So our assumption is only good if the amount of virus is large compared to the number of cells being infected. That's usually, but not always, true. And so we can come back later and ask the question, does it make a difference whether we assume that the virus is used up or not? Okay. And now we're going to use this simple example to learn how Tellurium works. So Tellurium defines the model as a string, a character string, and to define a multi-line character string in Python, you use triple quotation marks. You can either use single triple quotation marks or double triple quotation marks. Here we use single ones. And so we were going to write model string, this is just a string variable, equals triple quote, and then our model specification is in between the triple quotes. Okay. And then we're going to have a set of very simple Python commands that are going to load this model. te.loada of model string loads and parses that model and compiles it. m.simulate is a method that simulates that model for a given amount of time, from time 0 to time 10, and it uses 100 intermediate points. It's a fixed time step for this particular simulation. And then there's a method m.plot that throws up the results of that simulation. Okay. And we should have here in this cell here exactly that code. And we can try running it. You click inside that cell, hit Control Enter. It should think for a while. And then it should display plot. Did that work for people? Were people able to get that to work? If anybody is not able to get that to work, let me know and we'll go over it. All right. So let's go through this code line by line. It's not very lot of it. Import Tellurium as TE, as we mentioned, loads the library for Tellurium. We specify an Antimony model string using model string equals, triple quotes, and triple quotes at the end. Anything inside is not in Python, it's in Antimony, different language. And now we're going to take our concept, T goes to I1 at a rate beta times T times V. And we can convert that reaction into a pair of ordinary differential equations. dt by dt, capital T by d little t is equal to minus beta TB, because we're losing susceptible cells. For creating I1 cells, the I1 by dt is equal to beta T times V. Notice the sum of T and I1 is a constant. In Antimony, we specify this pair of ordinary differential equations by a transition rule. E1 is the name of the equation, and that's useful because it will return the derivative, the time derivative, so we have access to that. Colons are used to separate components of models for names in Antimony. T goes to I1. Semicolon defines the rate, beta times T times V. So if you look in green, E1 colon T minus caret I1 semicolon beta star T star V, and another semicolon. Semicolons define end of line as well. Okay, many of you have seen this before, maybe not everybody. That's all you need to know to be able to write rate laws. If you wanted to write the ODEs independently, you could write it this way, E1A, T goes to nothing. T goes to nothing means that there's a minus sign in front of it, beta times T times V. nothing goes to I1 means there's a plus sign. So this is beta times T times V. So that's writing the second set of equations. Why would you prefer to write it this way? Sorry. Why would you prefer to write it the first way rather than the second way? The first way, the mass balance is taken care of automatically. This one statement here gives you 2 ODEs. If you do it the other way, you have 1 per ODE. But keeping track of mass balance is sometimes a nice thing. Any questions on that so far? It's better to use the mass balance if you can. But it depends on what you're doing. If you have a regulatory reaction where chemical is not used up, then you'll use the form here. Nothing goes to I1 would be the form for regulatory interaction. That was covered in great detail with Herbert's class. I won't have time to go into all of that detail, but if you're interested, it's discussed in some detail in the manuals online. Herbert also has a really good textbook, and the lectures from last week are also available online. So we can definitely talk about those issues. Is antimony used mainly for reaction-based ODEs? Well, antimony can only write first-order rate laws. So everything is in the form of d something by dt equals something. So in that sense, yes, I'll come back to that. Yes, double slash defines comments, exactly. But you don't have to write reaction-based ODEs. You can write any ODEs you like. The chemical reaction format is actually more fundamental than the ODE format. If you had Herbert, he could give you a long explanation of why it's preferable to write things with arrows rather than as ODEs. As an example, if I write a set of chemical reactions, I can immediately derive the ODEs for them. However, if I give you a set of ODEs, you cannot back out the reactions that give rise to them. And I sometimes in classes will give that as an exercise. I'll take there's a beautiful paper by Tyson on cell cycle where he gives all the chemical reactions in the form of ODEs. You cannot determine from his paper what the reactions were. It's not possible. So that's an example. So in any case, for purpose, you can always write ODEs if that's what you want. Okay, so we've specified what the reaction is. T goes to I1, and we've specified the rate. And so the basic form of a specification in antimony is a name of reaction, colon, what the reaction is. And remember, if you want to write just an ODE, you would leave out the T. If I don't have that T there, and I have arrow goes to I1, that's equivalent to writing di1 dt equals. And then instead of an equal sign, you have a semicolon, and then the rate law, and then a semicolon at the end of the line. Okay. And that's all there is to writing ODEs or rate laws. You just write a lot of them, write a stack of them. And that's all we'll do this afternoon. And that's basically all the syntax you need to write antimony. It's very, very simple. Okay. For each parameter or variable, we have to specify the value. And so we'll have a section called parameters. Here's the comment. The comments are double slash. Parameters, and we define beta. And we're going to use the value 6.2 10 to the minus 5. And we're always going to try to remember to write what the units of our parameters are. In these models, we're going to measure time in days. And here our unit is per TCID. And I'll come back to what TCID is in a few minutes. It's a way of measuring viral loads operationally per day, because it's a rate. And we're going to use the number 6.2 times 10 to the minus 5. And that number comes from a paper of Amber Smith, and it's related to influenza. You could use any number you like right at the moment. We're going to specify the initial concentration of virus. We're going to make that here 10,000. And we're going to specify the initial number of cells. We're going to use 10 to the 7th cells. That number in a sense is arbitrary, could divide the amount of virus, the number of cells by 10. It wouldn't really change anything. And in this case, we're going to set a constant T0 because we're going to need it again, and then set the initial amount of T to be equal to T0. If we don't specify the value of a variable in Antimony, it'll set it equal to 0, but it's always better to specify it. If you don't specify the value of a parameter, Antimony will throw an error. Okay, any questions so far? Okay, this is about model specification, parameter values. And then we're going to run it. As I mentioned, there are essentially minimal 3 things you have to do. And now we're in Python. In Python, to run an Antimony model, we have to load the model, and that uses the te.loada command. So we say m, going to be a handle for the model, equals te.loada, parenthesis, model string. Now, we could have called model string anything we like. We could have called it a flu model, for example. And if we'd done that, we would have said te.loada, parenthesis, flu model. Similarly, we could make m any variable name we like. So we've now loaded the model in. And one thing that's going to be very convenient using Antimony is that all of the variables and parameters in the model are accessible through this model object m. So for example, if I want to know what the value of t is in my simulation, m.t will give me the current value of the variable t. m.t0, this is a parameter, will return the value 1e7. More interestingly, m.e1 will give me the derivative. That will return beta times t times v. And I can use this either on the left-hand side of an equal sign. I can set that value equal to something, or on the right-hand side to read it out. And so everything that lives inside of my Antimony model is directly accessible through Python with just a single dot. Okay? And we'll have plenty of practice doing that. Okay, the next thing we're going to do is run the simulation. We've loaded it, but we haven't executed it. There are 2 basic simulate commands in Antimony and Tellurium. We're going to use one of them today. M.simulate is a straightforward ODE solver integrator. It has a variety of settings which we're not going to explore. If you're interested in all of the many settings for simulate, you can look on the online documentation. For our purposes, what we need to know is that simulate starts with a start time, and then it has comma end time, comma the number of points. So this is a fixed time step integrator. And if you have a situation where it crashes, typically you make the number of points bigger for conversion. Again, there are fancy things you can do with the integrator, which we won't talk about today. There's also at least one stochastic method. Gillespie will do a Gillespie stochastic solution of the same equations. And so if you're interested in stochasticity, you can try that. We're not going to try that today. So we run m.simulate, and that returns an object which is, somebody asks, does stiffness affect the solver selection? If you're running stiff equations, there are all sorts of tricks that you have to run through. We're not going to run any stiff equations today. Again, I refer you for those kind of technical details to the Tellurium manuals. The Tellurium uses a standard ODE solver package called CVODE, which is quite elaborate. None of the simulations we're going to run today are stiff. But in principle, if you have stiff equations, you have to play games. A good point. Okay, m.simulate returns an object. That object has a slightly complicated form. Each of the columns of the object is named. So they're headers that contain the variable names. and then the values are underneath. One of the things that we may have to do later on is do some slicing to determine where things are. But for today, we're not going to need that. We're not going to need to do that. Okay? The nice thing, the disadvantage of having a complex object like this returned by the simulator is that it's not a simple NumPy array, and therefore some NumPy functions won't like it because they'll get confused by the character strings at the beginning. But it does mean that the array itself contains a description of what it is, which is why when I do a plot, it can put time, variable, and cell population in automatically. In this case, I put them in by hand, but in fact, it'll put them in automatically because it knows what the names of the variables. Okay? And then we're going to do a plot. And here, m.plot will plot it, and it gives me a little key with the names of the variables identified. Again, for plotting, you can certainly use any matplotlib functions that you like. The Antimony Tellurium m.plot command is very simple. It has some functionality, but not quite as much as the full matplotlib library. On the other hand, using it is simple. All right. The next thing that we're going to talk about, and this is the only Python we're going to do today, is that we're going to talk about, and I assume people have seen a little bit of Python either from last week or their own lives or Andy's course. The only Python we're going to do today is that we're going to do some parameter sweeps. And so for parameter sweeps, we're going to use either range or NumPy range function. And so we'll say, we'll load a model, m equals te load a model string for parameter value p in range, here using classic range, not NumPy range, 0 to 6. And then we have to remember a couple of simple functions that we're going to use repeatedly with respect to Tellurium. m.resetAll resets all of the time and parameter values and variables to the values that are specified in the model string. m.v is the amount of virus, initial amount of virus in the simulation. By default, it was set to be 10,000, but we can change it, and here we'll make it 10 to the p. So the first time we iterate this string, it'll be 0, and so we'll set the amount of virus to 1. The second time, it'll be 1, so we'll set the amount of virus to 10. The third time, 2, 100. Fourth time, 3, 1,000. Fifth time, 4, 10,000. And then it stops when you get to 6. It doesn't do the 6. We run s.simulate, m.simulate to get the results. We'll do m.plot with show equals false. That puts the data set into the frame buffer. It doesn't display it. And then we'll use te.show to display the result. Okay. So we reset the variables to their original values. We assign a new value to the parameter v, in this case, the variable v, initial value v. We simulate the model. We add the plot to the stack, but don't show it, and then we show it. Okay. Why doesn't everybody try actually running that? So there's a little exercise now. We can do that together, which is I want to copy the code that I've got there into the simulation that I have here. Okay, everybody do that. So I'm going to take my code here, and I'll copy what I've got typed there for p in range 0, 6, colon. Remember, Python cares about indentation. Jupyter will automatically indent things properly unless you force it to do something wrong. m.reset all, open close parenthesis, m dot v equals 10 to the p. Now I need my s dot simulate indented. And now in my plot, I need to indent my plot, and I'm going to have to add here show equals false. I know quotes. And now I want to undent, and I do te dot show. Okay, everybody follow along if you can. And now we'll run it, and what do we get? That's what I get. So I want everybody to try that and see that they're able to get it. And nothing we're going to do today is going to be more complicated than what we've already done here. The models we're going to use will get more and more complicated, but the code won't get any more complicated. In other words, we'll add lines to that little simulation. We'll add ODEs or reactions to that simulation, but the code won't get any more complicated. Can you explain m dot plot show equals false? So one of the things that a plotting program has to do is decide whether it puts plots in the same window or in a different window. If I put show equals true, what would happen is each time it runs, I will get a different plot. Okay. So show equals false will make the simulations overlay rather than be in separate windows. There's a comment that the legend should be changed. That's absolutely true. The legend isn't helpful in this case because I have the same legend from each one. Ideally, I would have the parameter values tagged to the color-coded plot. All of that is explained in the online documentation. We're not going to take the time right now to go through that, but yes, absolutely, one can do much prettier plots than the ones we're going to do today. This is a quick and dirty way to do it. But I definitely encourage you to look about how to use the plotting functions. They're quite sophisticated. Basically, they're all based on matplotlib, which is a relatively sophisticated package. The advantage is you can plot things in almost any way you want. The disadvantage is it's complicated to learn. But the basics are simple. So we're going to stick with the very simplest possible plots for today. But absolutely, we can come back and cover more elaborate plotting approaches. Okay. So one of the things in this simulation that we've seen is that we have both the number of uninfected cells and the number of infected cells showing up at the same time. And that's a little bit hard to see on one plot. So Tellurium has a very simple way to select columns without having to do slicing. And the way you do that is using, at the end of the simulate function, you use square brackets. That means it's a list. And inside of the square brackets, you put the parameters you want to plot. So here I'm going to put time, which is a reserved variable, and then the name of the parameter, the variable that I want to plot, in this case, I1. Okay, everybody try that. Run it. Oops, I typed something wrong. Float object is not subscriptable. Ah, typo. I put a period instead of a comma. Yeah. And so now I have just the number of infected cells versus time. Everybody try that. And why don't you also try plotting the number of uninfected cells, the number of T cells? I'll give people a minute. I'll give people a minute to get that running. Are people able to get that to work? Okay, great. All right. So that's the total content that we have to have for all of this, for all of the simulations we're going to do this afternoon. Now I want to come back, and you can continue to play with that a little bit if you like while I talk, to talk a little bit about the way viruses work. And I'm going to be basing all of the simulations I'm going to do today on experiments that were done by Amber Smith. I mentioned her before. She's at the University of Tennessee in Memphis Medical Center. And she has done some very nice, careful experiments on flu infection in mice. And so she takes her mice, she exposes them to flu, she measures the amount of virus in the mouse as a function of time. And what you see is that there are 1, 2, 3, 4, 5 regimes of viral infection. You could maybe say 6 if you want to be pedantic about it. There's a phase 1, an early phase, which is called a lag or an eclipse phase, during which the virus has entered the cells, is beginning to replicate, but hasn't been released by the cells yet. There's a phase which lasts for about a day and a half to 2 days, when there's a rapid exponential growth of the amount of virus. During that phase, if you got the flu, you wouldn't feel sick. You wouldn't know that you were infected. Then phase 3 is actually what's called the peak viral load. That happens typically around day 2. And that's the time when, in particular, interleukin-2 and interleukin-6 will kick in. The interleukin-6 means that you'll get a fever and a headache. And so with flu, by the time you actually get your first symptoms, you already are at your peak viral load. Then there's a period of about 5 days over which the amount of virus goes down. Notice that this is on a log scale. So going down slowly here is actually going down pretty fast. The amount of virus goes down by a factor of about 10 between day 2 and about day 7. Then starting on the end of day 7, there's a rapid decrease in the amount of virus, also exponential but much faster. And then in usual cases, the virus is cleared and the amount of virus goes to 0. The unit here, TCID, may be unfamiliar if you're not working with viruses. It's not possible in general to measure the amount of virus directly, at least it used not to be. And so the amount of virus circulating was defined operationally by taking the sample from the infected individual, and then putting that virus into additional individuals and finding out whether they die or not. And then you do sequential dilutions by factors of 10 to determine the level at which half of the infected individuals die, or if you go into tissue culture, half of the cells in the tissue culture die. Got that? The details are not that important. What we need to know is that the TCID is a measurement of the effective damage produced by that amount of virus. It's not calibrated to a specific concentration in moles of the virus or specific number of viral particles, but it is a measure of how much infectious virus you have in your system, and it's linear. So if my TCID is 10 times higher, I have 10 times as much virus. And so really, for our purposes, what we need to know is that the TCID gives us a linear measurement, but there's a proportionality constant that we don't know. And if you want to look it up in more detail, actually, Wikipedia has a quite good article on how to TCIDs and what they mean. Okay, so coming back to our curve, it's almost invisible in this plot, but it's quite important. There is a period of time during which there's no production of virus. That's the eclipse phase or latent phase. And for flu, it lasts about 6 hours. So your cells, once you're infected, somebody coughs on you, your cells take up the virus, but they don't start producing any virus for about 6 hours. In the case of COVID, that number is a little bigger, probably more like 6 to 12 hours. There's second, an exponential growth phase. In flu, that lasts about a day to 2 days. And what we'll notice is that during that period, the amount of virus in TCID goes from 0 to 6. That is, the amount of virus increases by a factor of 1,000,000 over about a day and a half, or a little bit faster, and which means that the virus increases about 10-fold every 4 hours, or, since we're measuring time in days, 10-fold every 1/6 of a day. And that goes on for about a day. And the time over which a phase lasts is important, those we have to note. And the rate of exponential growth or decrease is something we have to note. So we're basically reading off all of the information from this graph that we can find. The next thing that happens is saturation. That's the maximal viral load. In our case, that happens around day 2, day 1.5 to day 2. And the saturation is at 10 to the 6th, 1,000,000 times more virus than we started with. Got that? Then over the next 5 days, the amount of virus goes down by a factor of 10. And so what that means is that we have a 10-fold decrease over 5 days. And that period lasts for 5 days. That's our region 4. Region 5, we see a faster decrease. Over 2 days, we go from 10 to the 5th back to 10 to the 0. So we have a 10-fold decrease every 2/5 of a day. And so again, we characterize the virus in the following way. For 6 hours, we have no viral production. We have 10-fold increase per 4 hours over the next day. We have saturation at 10 to the 6th at day 1. We have 10-fold decrease over 5 days for the next 5 days. And then we have a 10-fold increase, a 10-fold decrease over 2/5 of a day for 2 days. And then we have no more virus. And so that's essentially a full description of what's happening in this viral load curve. Now, if we had better experimental data, more experimental data, for example, on cytokines or T cells or macrophages or other things, then we could do a more elaborate model than we're going to attempt today. But for today, that's the data we're going to work with. And we can already do quite a bit with that. And I should say that there are data available on those things, but for today's purpose, we're not going to focus on it. And so now, based on that pattern that we just identified, we want to build a model of that reproduces it using ordinary differential equations. So what we need to do is to identify what the key variables are, especially what the key biology is, and we're going to build this model sequentially, piece by piece, and make sure that we're able to reproduce the experimental results. So to begin with, we're going to replicate what we had here in our cell population data, and we're just going to think about viral replication and infection. Viral infection and replication is actually pretty complicated. For SARS-CoV-2, a single-stranded RNA-positive virus, the viral life cycle looks like this. We're not going to deal with the complexities of RNA replication, protein synthesis, packaging, or anything else. We're only going to consider the affinity of the virus for the receptor on the surface of the cell, determines the rate of infection, that's the beta parameter. The time it takes from the first infection here to the time of viral release, that's the eclipse time, and the amount of virus produced per unit time by an infected cell. Those are the only things that we're going to take away from this intrinsically rather complex process. We definitely, tomorrow and the next day, will go and lift some of those simplifications and deal with perhaps a more realistic model. But for now, we're going to stick with the very simple. Okay. To begin with, we're going to do our infection model. This is the one we've already done. We're going to start with population of uninfected susceptible cells, T number, initial number T0. They're going to become infected at a rate beta times T times V. And as I mentioned, in reality, when a cell becomes infected, this virus that's infecting it is used up. And so perhaps we should really write a rate law where T plus V goes to I1, rather than simply V regulates T going to I1. And we'll try that as an exercise. Okay, good question. We've mentioned a couple of other biphasic and triphasic viral load curves. How does the mouse influenza model translate into humans? In the case of influenza, the viral load in humans would also be biphasic. So the detailed amplitude and the rate of replication might be slightly different. The clearance times might be slightly different. But the basic pattern of eclipse followed by exponential growth, maximum around day 2, 10-fold decrease over 5 days, followed by rapid clearance would be the same in mice and humans. It would not be the same in bats, which is significant. Good question. Okay. And I want to make a side comment here. And the figure seems to have gotten broken here. I don't know what happened. PowerPoint sometimes does that. Which is that if we think ahead to cellularizing this model, the statement that the uninfected cells become infected at a rate beta times the number of uninfected cells times the amount of virus seems innocuous. But in fact, it's not a meaningful statement. And the reason for that is that a cell, in reality, can only measure something that it has access to, which is the amount of virus in its local environment. And so we should be writing that rate law in terms not of the total amount of virus, which the cell can't possibly know, but rather the amount of virus per cell, which is V divided by T0, the amount of virus divided by the total number of cells. And in that case, our rate, beta, becomes beta times T0. And so even though beta times T0 times T times V divided by T0 is just beta T times V, when we cellularize it, we'll need that second form. We're not going to use that second form today, but I want to let you know that you have to think very carefully when you write these ODE models, because it's very easy to write something that doesn't make sense. The fact that you are looking at aggregate quantities, like the total population of infected or uninfected cells, the total amount of virus, hides some of the biological reality. That means it's very easy to write a model that makes mathematical sense but doesn't make biological sense. Okay, so now we're going to go back and run the simulation that we just ran. And what I'd like to do here is actually begin to upload the larger model, which we have created for you. There's a Jupyter notebook which has all of the results that we're going to be using today. We can type them in by hand by ourselves, but to save some time in case we run out of time or otherwise we want to do something with it. Let's see. We're going to lose our parameter scan, so let's see. I'm trying to think if I can copy that somewhere. I would suggest you take that little, if you don't want to have to retype it, grab your little code for the parameter scan and put it into a notepad or something else on your desktop so that you have it available to paste back. Okay. I will also paste that code into the chat. Paste that code into the chat so that you have it. All right. So now we're going to go to File, go to Open, our usual. We're going to go to Upload, the same directory we had, so you should still be there. And then we're going to select Module 1.5, How to Write a Viral Infection Model. We'll upload it. We'll open it. And you should get that. So I'll wait a minute to make sure that everybody has that. And this is a notebook that Josh prepared, and it's very nice. It has the experimental time series plotted in it and a variety of other things. Okay, it looks like most people have gotten it. Does anybody need more time? If you do, raise your hand or type in the chat. Okay, one or two people say they need more time. Okay. And so now we can go into this nanoHUB window. We've got that viral load curve. Here are comparable data for SARS. These are now not in vivo data, but in vitro data. So this is in cell culture. There are no immune cells, single type of cell, happen not to be lung cells, but you can see something similar. The amount of virus stays to 0 for about 6 hours. It increases exponentially over the next 6 hours. Notice that it doesn't increase as fast as for flu. And then it saturates, keeps going up until about 36 hours, and then it comes down again. So this would be what Amber Smith would characterize as a monophasic response. But remember that this is occurring in culture without the immune response that you get in a living, in the intact animal. Does anybody else need more time to get things working? I think everybody's got it. So this is the simulation that we just ran. It's notebook cell number 35. Why don't we all navigate to that? And let's hit Control Enter to run it. And we get our cell population. All right, so we've recovered exactly what we did before, nothing additional. Okay, so now we have a little exercise, which is actually the one we already did, which says change the value of beta. And we already did a parameter scan where we changed the value of beta. But let's go back and do it now here. So I'm going to take the text, the code that I kept for my parameter scan. And I'm going to paste it in here. The one problem with using a larger font is that then the lines tail off. So I'm going to type for P in range. And the instructions are to go m beta times equals for beta equal e to the minus 2, e to the minus 1, 1, 10, and 100. So I'm going to have to make a little bit of a change from what I had there. I think people can probably figure it out on their own. Let's just make it here. I'm going to make range from -2 to 3. And I'm going to set m dot beta equal 10 to the p. And let's see what happens. Did I do it right? I forgot to multiply by my original value of beta, didn't I? So let me do it a different way. Let me say for p in range 0, 6. You guys can work this out yourself. You don't have to follow what I'm doing. I'm probably making a mess. I will say to begin with, let's see, I want m beta to be 10 to the minus 2. Josh, that's actually a little more complicated perhaps than we thought. Here's a good, okay, so we've got the m dot v. I'm going to use a range to do it, but you can do it any way you like. Anybody have any luck getting this to work? M beta times p will work, yes. So we could say m beta, so we could say m beta equals m beta times 10 to the minus 2, minus 2 to 3. See about that. So here we'll get m beta will be its initial value starting out times 10 to the minus 2, and it'll stop at 10 to the 2, so that should be right. There we go. Thank you. I'll let everybody try that and see if we can get that to work. I suggested using NPI A range, but let's not take the time to do that right now. If you're not familiar with the NPI A range function, it's Python, for some reason, in the default Python only has integer ranges. And so you have to use a NumPy extension to be able to do non-integer steps in a loop. Sometimes you wonder why programming languages leave out basic things like that, functionality like that. I can't tell you why Python left out something that basic, but then again, it also didn't have arrays. So NumPy had to invent arrays for Python. So there are a couple of places where Python, I guess for philosophical reasons, left something out that I would have thought was pretty basic. Okay, looks like most people have it now. Well, there are lots of ways you can loop over floats if you want to, but and you're welcome. I mean, you're certainly not limited to using the basic, very, very, very basic Python we're going to use today. So for the exercises, you're absolutely free to use any methods or classes you want. You've got two graphs for some reason. You sure you've got show equals false turned on? Okay. I'm not sure. Are you using nanoHUB or are you using a different IDE? Okay. I can't tell you. Did you get the same data sets though? You got two plots, but that's possible. Okay. Yeah, that looks fine. Yes. The plot line would be the one that would be doing it. If you're getting two plots, that must be because you have the only plot function is one. You should only get one plot. If I make it too much bigger, you won't be able to see here. Let me take out the title and everything else so that we don't have the line extending over the edge of it. Yeah. That's all the code we wrote. Okay, remember, import Tellurium is TE, import matplotlib. Here he's just imported pyplot, so it didn't import. It's okay, we're not using it. Model string, definition of the model string. We're scanning P between -2 and 3. We're exponentiating to the P, multiplying the initial value of beta by that, simulating with that new value of beta, adding it to the plot to show false, and then showing the result. Ah, yes. Good. All right. What about using up virus? I mentioned that when a cell becomes infected with virus, actually the virus is used up. If we want to see what happens there, it's really easy. We simply say that instead of having T go to I1, we have T plus V go to I1. That's all you have to do to change the results. This is one reason that it's easier to do things with reactions than it is to do them with chemical rates. I mean, with chemical reactions rather than ODEs. So make this change. Add plus V here. and run it again. Didn't make a big difference. What if we look at the amount of virus? The amount of virus is constant. Let's see. Why is that? Did I outsmart myself? Beta times 2 times 3. Plus I1. Initial amount of virus is 10,000. And here it stays constant. Well, I got something I didn't expect. I hadn't tried this one out. I had set it up for us to do together. Let's take this out. And let's not plot V, but let's actually plot the whole, all of my variables. Something interesting is happening here, because it is not reloading my simulation. Oh, what's missing here? Somebody? Yes, thank you. Perfect. I managed to delete the load model from my simulation. There we go. So now let me put it back the way I had it before. There we go. All right, so this was our base simulation. Thank you very much. And now we're going to have a chemical reaction type term where the virus is used up when it infects the cell. And what's going to happen? Anybody? Thank you, Jingmei. That was very good of you. Look, now the number of infected cells goes down much more rapidly. What happens if I look at I2, I1? Goes up very fast. What happens if I look at the amount of virus? The amount of virus goes down very fast. So if I were going to use this model, I would have to recalibrate beta significantly to be able to make it work. So we're going to work with the base model that we started with, which is T goes to I1 without adding the virus. All right. So it's not very exciting, that model, one reaction. So now we're going to begin in the next couple of minutes, and we're going to run out of time. We're going to ask, I may ask you if we can run over by a few minutes. I know for some people the time zones are bad, and so I certainly don't want to talk for forever, but I want to get a little bit further before we break for the day. I'd like to talk about eclipse phase. Remember that we said that the initially infected cells don't release virus. It takes time for the virus to synthesize its own genome and to synthesize the proteins needed to package the genome and to assemble them and secrete them. And so there is a delay between the time a cell becomes infected and the time it starts producing virus. And so we're now going to introduce a cell type, which is I2, which are our virus-producing cells, virus-releasing cells. And we're going to have a transition between our early infected and our virus-releasing cells. And that rate, the infection is going to, that transition is going to happen at a rate K. K is going to be 1 over the eclipse time. The rate is inversely proportional to the delay. For influenza, the delay is 3 to 6 hours. For SARS-CoV-2, it's 6 to 12 hours about. And we're going to re-express those things in terms of days. So a 6-hour delay would be 1/4 of a day. And so that means that K will be 4. That is 4 per day for flu. And it would be about 2 per day for SARS-CoV-2. And we'll use K equals 4 per day to start with. So let's actually put that into our simulation. So what I want you to do here, and it's actually done out in the next set of, the next panel, but let's do it by hand first anyway. Let's add that transition. So the transition is I1 goes to I2 at rate K times I1. We write that, this should really be E2. We could have it, sorry, E1 is T goes to I1, and then we're going to add a rate equation. I1 goes to I2, and we'll have to specify the initial value by 2 and the value of the parameter, and I want you to now simulate that and plot it. And I'll do that by hand, but I would like you to try doing that. And then I want you to scan over the eclipse time, K. So you can do that on your own. I'm going to do it the way I come up with it. I may make a mistake, so I wouldn't copy me too carefully until you've tried it on your own. Right. Parameter. Okay. Okay. Yes, all of the videos will be made available as soon as we have them processed. Okay, and now I have a new variable, which is I2. I should have had I1 set to 0. Okay. Try that. Doesn't do anything for T. Let's look at all of my things together. Pretty hard to see. So let me not do my parameter scan to begin with. Remember that the comment, why was I1 not defined in previous simulation? If you don't define a variable, it's set to 0. And since I1 was initially 0, we could get away with not defining it, but it should have been defined. It's always better to give the initial values and not depend on the code to do it for you. Inputs and initial conditions are not anything that Antimony cares about. These were just convenience comments. I might have called this parameter values and this initial conditions here. But it was trying to specify, really, I would call this parameters. And I'd call this initial conditions, and then I'd move this down here. Actually, T0 is a parameter. I haven't done anything because these are just comments. There's nothing structurally different. But what I am going to do now is just plot the number of actually what I'll do is I'll turn off the range function for a moment. And I'll just plot the base simulation. All right. All right, so you should see something like that. Is T0 a parameter? T0, so what's the difference between a parameter and an initial value? There is no fundamental mathematical difference between a parameter value and an initial value. They're both numbers. However, parameters are things that are not going to change during the simulation, and initial conditions are the values of variables. And so in this case, the number T0 is how many cells I started out with, uninfected cells I started out with. And because I'm going to need to use that number later on, I'm making it a parameter and then assigning the initial number of cells to be that. I can put a semicolon here. That doesn't change the simulation that I'm doing at the moment, but it makes the number T0 available in the future. So there was a question about solving I'm not sure, I'm sorry, that question, somebody asked a question about solving, think about CompuCell and about fluid transport, but I'm not sure what that was referencing. So let's talk about that one later. I'm happy to talk to you about Navier-Stokes and Lattice-Boltzmann and so on. For the moment, we're not going to be doing anything quite that complicated. Okay. And so here I now have the simulation run for my single value, and what do I see? My uninfected cells in blue come down. They all disappear after a day. The simulation is basically done by 2 days. My number of early infected cells comes up, peaks, and then decays. And at the end of the simulation, all my cells are late infected I2 cells. So now what I'd like you to do is scan K. So now I can turn my parameter scan back on, do -2 to 2 again. And instead of scanning beta, I'm going to scan K. And I'm going to see what happens. It's a little bit of a mess here. So let me look at one of the variables by itself, time, comma. Which one shall we pick? You'll notice that the rate at which cells become infected is constant, doesn't depend on anything, because what we've changed is I1 goes to I2. That doesn't change the rate at which T's go to I1. So let's just plot I1 for the moment. And what we see is the following. As beta, if beta is very small, our I1 cells live a long time. And so we get a lot of them. That's this blue curve at the top. And as beta gets bigger, you have smaller and smaller humps of our I1s, and they last a shorter and shorter amount of time. If I look at I2, I'll see the opposite to that. If beta is very small, my number of late infected cells increases very slowly. If beta is large, as it increases, the rate at which my cells become I2 gets faster and faster. If beta is very, very big, it doesn't make much difference. Everybody be able to do that simulation? I'll give you a minute to try that out on your own. Okay, looks like everybody got that. Okay. So this was actually doing that simulation. We saw these results already. And we made beta change over a huge range here. We made it go from by factors of 10. In reality, we know that beta, the K value, it doesn't change that much. And so it might make more sense to say, let's see, let's try one more simulation. We said K is 4, that's in units of per day. So it might make sense instead of multiplying by P to add P. So in this case, if P, let's say, go from -3 to 3, in that case, K will go from 1 to 6. That's a more sensible range. You see, it doesn't do very much for the I2s, but if we look at I1, it actually makes a big difference. If K is small, our early infected cells last a long time. We get a lot of them. As K goes down, K goes up, the number and duration of those I1 cells goes down. All right. And I want to do one more small exercise before we break for the day. We have our virus releasing cells, but at the moment they're not releasing any virus. And we're going to do a very, very simple model that assumes that every cell releases P units of virus per day. So in this basic model, every virus releasing cell is releasing the same amount of virus, P. In reality, the viral production is much more complicated than that, but that's what we're going to start with. We can write that in the form of a rate equation. Nothing goes to V at a rate P times I2. Everybody got that? And then we can put it all together, and we're going to add a viral rate law. And we're going to, in this case, calibrate, to begin with, just use a default value of P, which is that the rate of production of virus is 1 unit per cell per day. And I'd like everybody now to write that as an exercise. And so what I want you to do now is add viral production. So I'm going to do it along with everybody else. Nothing goes to virus at a rate P times I2. This is virus production. Okay. We have to give a parameter value for P. We set it equal to 1. That's what PCID is produced per infected cell per day. Oops. That's the one problem with having it zoomed. It's hard to see. Okay. And we need to specify also the initial amount of virus. And now for this one, yeah, I think for this one it's okay. We'll start with this. Actually, in this model, we're going to change it a little bit. We're going to start with now with no virus, but with some infected cells. Okay, so we'll make the initial amount of virus 0. So we'll start with no free virus, and we'll start with some infected cells, some early infected cells. Okay, does everybody have that? The changes are here on the left in that window. Let's run that. I'm going to go back to having the range just be. We're not going to do the times. And I'm just going to plot everything to begin with. And you'll notice the virus starts out low and then keeps going up. And so if I want to see that better, it would be better for me to have a log scale. And it's probably a little small to see it, but let me show you how to do a log scale in the plot. To get a log scale in the plot, I do y scale equals log. And then because I don't want there to be zeros, I have to do a range. Y lim gives me the y range equals square bracket. Minimum value will be 1. Minimum value will be 1. Maximum value will be 10 to the 7th. Okay, we're going to stop in just 1 second. I know we're out of time. So let's run that. Okay. And let's just look at the virus for a moment. Okay, so that's our virus now. Okay, and what you see here is that there's a delay, a short delay, followed by an exponential growth, followed by a saturation. So this very, very simple model is replicating 1 and 2, parts 1 and 2 of our viral load curve. So what I'd like people to do as an exercise now would be to change that rate law, that delay constant, okay, and change P and see what happens, okay? And so your homework problems, if that's what we want to call them, would be to scan the values here for K and for P and see what happens. Let me just do that. I can do that easily enough here. I'll do -3 to 2 to 3. I'll run it. I see it doesn't make a huge change here. For the amount of virus, it delays a little bit. I could do my powers of 10 if I wanted, and see what happens. So I think that's going to be it for today. Tomorrow we'll pick up where we stopped, continue developing this model, and then when we have the model pulled together, we won't go through all of the steps of model development. They'll be available online. But when we have that model pulled together, we'll put it inside of CompuCell and start turning it into a spatial model. Was everybody able to follow that more or less? Let me do one more poll here before everybody breaks and just ask the question, were people able to keep up with the exercises? Because I don't want people to feel that they're left behind. You don't have to answer all those other questions, at least whether you were able to do the exercise. Okay, so people who got stuck or had problems, please do contact us, and we will do our best to walk you through anything that you got stuck with. You can absolutely get CompuCell to run on your laptop. Is it a Mac or a Windows laptop? If it's for either Mac or Windows, there's a one. Okay, Macs are a little bit more complicated. The information for installing CompuCell on the Macs is there on the CompuCell website in detail. If you have some issues with security getting the installer to work, ask one of us. Again, that's why I understand the problem and the frustration, but the reason we're using nanoHUB is to avoid this problem. I'm not sure what could be happening with Python on your Mac. I know Spider doesn't run reliably. For example, the Spider IDE doesn't run reliably on Macs. Okay, thank you, everybody. I understand that with time zones, there can be a lot of people who are up very, very late or in the middle of the night. And so I really appreciate your patience in joining us. I understand that it's a struggle to be on this call. The times were selected to be at least roughly tolerable for Europe and not as horrible as possible for Asia. But there's no time, unfortunately, that works for the whole world. And I do appreciate you joining us. I hope I'll see everyone tomorrow morning at 11. And if there are any questions, comments, how we can make things better, please let us know. Okay. Look forward to working with you, and we're looking forward to showing you how to build CompuCell models of viral infection and of other diseases. So that's the end of the official program. You're welcome to stay on if there are questions, comments that you'd like to have now. Otherwise, we'll see you tomorrow morning.